Welcome everyone to Bileşik Algebra and Number Theory Seminar Series. And with my pleasure, today's speaker is Professor Toshiki Matsusaka from Kyushu University and friend of mine. I'm very happy to
Mhm.
see him. And he will speak about the interaction of number theory and topology through modular nodes. Thank you.
Yeah, thanks so much. Yeah, I'm Toshiki Matsusaka from Japan. So, nice to meet you. So, yeah, I'm very happy to have an opportunity to give a talk in this seminar, yeah, international seminar. Yeah, so today I'm going to talk about the study of modular knots from the viewpoint of number theory and topology and its connections. It's very interesting connections, and this work is joint work with two Korean mathematicians, the Sunni Kang and Kyungbae Park. The first I noticed that our article is already available on archive. The title is on the Alexander polynomial, so modular knots. So please, if you have interest in them, please visit the archive and Google its title. The and my talk slide is also available on my webpage. So if you want to get the PDF, then please visit my webpage by Google my name, Toshiki Matsusaka, then maybe you can find the PDF on the top page, the English version of my webpage. So these two collaborators are professors in Gangwon National University in Chuncheon, Korea. And actually, I was also there last year as a visiting professor. So then at that time, we started this joint project. And yeah, Sunny Khan and I are the number theorist, and Gyongbe Park is a topologist. And this work is a collaboration with these two different topics, number theory and topology. So the main topic, modular knot, is a knot, a kind of knot defined on the three-dimensional space and defined by using some information about the real quadratic irrationals or some binary, indefinite binary quadratic forms and so on. So yeah, this is the modular knot. This green curve is an example of modular knot, and we can find this very beautiful picture in Josue's webpage titled "The Mathematical Imagery." Yeah, in this web page, he provided many pictures about modular knots or many other mathematical objects like fractal geometry or something. Yeah, you can find many beautiful pictures about the mathematical object. Oh, yeah. But anyway, let's start the mathematical topic on modular knots. So the first I begin with the classical motivation on the study of modular knots is related to the Gauss result on binary quadratic forms. So as you know, the Gauss studied a set of binary quadratic forms and it's some theoretical background. So let Q be a set of integer questions binary quadratic forms, ax squared plus bxy plus cy squared, all questions are integers. And as you know, the modular group acts on this set from right. And we call a class invariant. We call a map defined on this quotient space a class invariant. The value is taken in a certain set. For instance, if x is integer, then the classical example is a discriminant of the quadratic form defined by b squared minus 4ac. Now then maybe you have already studied in high school or somewhere the this yeah, but the action is not. But the discriminant is indeed invariant under the action of S0 to Z. So then this this map defines a well-defined map on this quotient space, and Gauss studied such a type of class invariance. For instance, if we fix a discriminant D and consider the subset QD consisting of quadratic forms with discriminant D, then Gauss showed that the quotient space have some group theoretic structure. For instance, for a generic discriminant D, then he found a certain composition rule, and he showed that this group admits the finite abelian group structure, and often we call its order class number. Actually, in the modern context, the class number is often defined by using the notion of ideal class groups of number field. But for the classical case of quadratic fields, these two definitions are essentially the same. And yeah, here I provided one example discriminant, but I think in the long history there are many types of class invariants have been studied by many mathematicians. And in this talk, we want to study a kind of topological invariant of class invariant of this quotient space coming from the topological theory. The another example of the class invariant is the closed geodesic defined for a very special, the positive discriminant case. So in this slide, let D be a positive discriminant with such that this is non-square. Then we can define for each binary quadratic form, we can define the closed geodesic and we can consider its length. And this gives a real valued class invariant. To be more precise, since the discriminant D is now a positive non-square, then the binary quadratic form Q have two different roots, two distinct real roots, W and W prime, and they are Galois conjugates to each other. Then on the upper half plane, we can consider the geodesic under the usual hyperbolic metric defined on the upper half plane, that connecting these two roots. So on the upper half plane, this geodesic has an infinite length, but if we consider the quotient set, then we can define the finite length closed orbit, so-called the closed geodesic. Here, as you know, the quotient set H, the upper half plane over SL2Z is homeomorphic as a topological space sphere except for one point corresponding to the cusp I infinity. And we know that by using the metric defined on the upper half plane, we can compute the length of its closed geodesic closed curve, and we know that the lengths have some information about the unit of the integer ring of real quadratic field. So this is a kind of classical connection between the topology or geometry and number theory via the geodesic. And such types of class invariants often called the geometric invariant because we use the metric. And such types of geometric class invariant have been studied by many mathematicians. For instance, recently Duke Imamoglu and Todd in 2016 in their annals paper, they introduced a new type of geometric invariant and studied some number theoretic object like a L function or something as an application of their new geometric invariant. But our main topic in this research is the topological class invariant by generalizing the notion of geometric geodesic to the knot and applying some knot theory to such a rift of closed geodesic. The topological means that we don't use the metric or something, and we can use continuous deformation and so on. So this is the motivation, and in the following 4 slides, I will explain the brief history of modular knots. The modular knot was already introduced by the Etienne Ghys, the French mathematician, and there are some studies about modular knots. So in the first section, I will give some introduction about modular knots. So the fundamental fact is this homeomorphism. So as I explained, the quotient set of the upper half plane over SL2Z is homeomorphic to the sphere without one point. But if we take a lift from the upper half plane to SL2R, then we can get some three-dimensional manifold. As you know, the SL2R is a subset of R4. So this is an object in 4-dimensional space, but by the condition determinant equals 1, this defines a 3-dimensional manifold. And by taking the the quotient by the action of lattice, we get some more complicated three-dimensional manifold. But by Milner, he showed that this quotient space is homomorphic to a certain knot complement in three-dimensional sphere. Here, this knot is given by this trefoil knot. And this provides a certain natural lift of this Riemann surface to the three-dimensional space. Yeah, this is a fundamental fact. And Ghys considered this space and a certain flow defined on this space, defined by this formula explicitly. Yeah, this defines a flow, and he called its closed orbit a modular knot. So each closed orbit a modular knot. Here I will explain in more detail. So now M is an element of this space. That means this is a matrix in SL2R. But now we regard this quotient space as a topological space. So then M is now a point defined on this quotient space. This matrix is also a point, and this product also defines a point. But now T is a kind of real parameter, the time parameter. So this matrix, this product of matrices defines a curve on this space. So M is initial point, and if we change T, then we get some curve. And sometimes for a very special initial point M, this closed curve, this curve defines a closed curve. That means there exists a certain positive time such that the position is the same as the initial point. And such closed orbit is called the modular knot. But what is the relationship between such a closed orbit and the previous geodesic, a closed geodesic defined on the Riemann surface? So the relationship can be obtained by a very simple observation. So as I mentioned, the closed means there exists a certain time such that the position at T coincide with the initial point. But now we consider the quotient space. So there can be a certain matrix gamma in SL2Z such that this equation hold. And this equation means the closed this curve is a closed orbit. So from the viewpoint of modular knot, we get this equation. But if we replace the main character from the initial point M with the SL2Z element gamma, then we can say that such gamma is diagonalized by matrix M. But as you know, the elements of SL2Z can be classified into three classes: elliptic, hyperbolic, and parabolic. And we know that such matrix, that means the character diagonalized by a certain matrix SL2R with real eigenvalues, are the hyperbolic matrix. Hyperbolic means the absolute value of its trace is greater than 2. So this observation says for each closed orbit, for each modular knot, we can get a hyperbolic matrix. But on the other hand, conversely, for each hyperbolic matrix, since this is diagonalizable, so there exists a certain M such that the M inverse gamma M is a diagonal matrix with real eigenvalues. So by using such M, we can define a modular knot. So in this sense, there exists a certain one-to-one or some correspondence between hyperbolic matrix and modular knot. And in fact, every modular knot can be parameterized by using hyperbolic matrix. For instance, this matrix is a hyperbolic matrix, and this picture can be found in Josue's website. But anyway, this matrix, from this matrix, we can get a modular knot. This green curve is modular knot. And this yellow curve is the missing trefoil. So now we consider the quotient space SL2R over SL2Z. This is homomorphic to the trefoil knot complement. And this yellow one is the missing trefoil. And this is modular knot. So for each hyperbolic element, we can get modular knot linking with the missing trefoil in general. But of course it's very difficult to explicitly compute the form of modular knots from the information of hyperbolic knot, a hyperbolic matrix. And we can also say that this modular knot provides a natural lift of the geodesic flow in this sense. So if we consider the map from M, it's an element of SL2R, to Mi, its action to the element of the upper half plane, then we can get a natural projection from the quotient space to the Riemann surface. And actually, for every modular knot, every modular knot is parameterized by hyperbolic matrix. So from hyperbolic matrix, we can get the geodesic, and yeah, on one hand, we get from modular knot we get the closed geodesic as a projection. On the other hand, from hyperbolic matrix, we get a geodesic and geodesic closed geodesic as a projection from H, and they are coincide. They are the same. So in this sense, this modular knot provides a lift of closed geodesic. So, and for instance, the length of closed geodesic have some information about the real quadratic field. So then we can guess that. So this topological object, modular knot, also have some information about number theory or something. And in this research, we started such a research about the connection with the real quadratic irrationals and topological invariants. But as the first step, actually, Ghys himself already studied some topological invariant of modular knots, the linking number. Yeah, he studied the linking number of modular knots and the missing trefoil. So in this case, for hyperbolic element 1112, the corresponding modular knot is a trivial knot, this green one. And combining the modular knot with the missing trefoil, we get a link. It's a two-component knot, the union of two knots. And then he studies the linking number of this picture. Here, the definition of the linking number is very simple. Here, I will give it in the combinatorial way. But first, we assign some suitable orders to every component. Then, just counting the signed intersections, we get the linking number as the average of the intersections. For instance, in this case, the picture has no orientation, but if we fix the orientations of these two components as this crossing becomes -1 crossing, then by induction we get this one is +1 crossing, this one is -1 crossing. So there are 6 crossing with signs, and by taking the sums, we get, in this case, the linking number equals 0. So for each modular knot, we can get some integer value. And actually, this linking number provides a class invariant, a topological class invariant. Topological means this class invariant comes from the topological object. And Ghys showed a very beautiful theorem. This linking number appears as the modular gap of log delta function. So here delta function is the usual cusp form of weight 12. And if we take the log, then log delta function is not modular form, but the modular gap, the difference from the modular transformation law, can be expressed in terms of linking number. So the linking number knows the information about the modular transformation of some function. This is very, very beautiful theorem, I think. And yeah, from motivated by this result, I guess that if we replace the linking number with other knot invariants like Alexander polynomials, Jones polynomials, where there are many types of knot invariants, then what happens? So for instance, Alexander polynomials knows So what does Alexander polynomial know? The real quadratic irrationals or number theory or something. So this is a schedule proof, but this is not main topic of this talk, so I skip the proof. But the important point is, so in the previous slide, I defined the linking number in combinatorial way, but actually the combinatorial definition does not work to prove such a theorem, because it's just the combinatorial definition uses the two-dimensional projection of knot, but so far we don't know the precise picture of modular knot. So
Yazdan beri bir yayın ilgili bir şey var mı ya?
so
Bugün
yeah.
veya gelecek Evet. Yani yayını 2025'in yayınlanmış bir şeyim var. Kaçın var?
Okay.
Now we're fine. Okay.
Yeah. So the important point is we have to redefine the linking number by using more abstract way. For instance, in this proof, we redefine the linking number by using the first homology group of something, and then by applying some known result about the homology group, we get the relationship between the linking number and the modular forms. But anyway, this is not the main topic. But the proof is very simple, just one slide. So the next, we want to replace the linking number with other topological invariant, and our main focus in this research is the Alexander polynomial as the first step. The Alexander polynomial is a polynomial valued invariant defined for knot. For instance, in this research, we want to compute a polynomial invariant for every hyperbolic matrix or real quadratic irrationals or something. For instance, for hyperbolic matrix 2, 1, 1, 1, this is corresponding to a golden ratio as it's a fixed point of this matrix. Then actually, this part is non-trivial, but from golden ratio, the golden ratio corresponds to unknot. And from knot picture, we can compute the Alexander polynomial, and for unknot, the resulting polynomial is just constant one. So by taking the composition from composition of this map and this map, we get a certain class invariant from real quadratic irrational or hyperbolic matrix or a corresponding binary quadratic form to polynomial. Other example is H352. This corresponds to this real quadratic irrational. And from this one, we get the trefoil knot. The trefoil knot have the Alexander polynomial to t squared minus t plus 1. So we get the map from the quadratic form to polynomial. And this gives a topological class invariant defined on this quotient space and polynomial. And the question is, what is this in number theory or something? But anyway, to define the Alexander polynomial or to study the Alexander polynomial, we need some notion or we need some basics of knot theory. So here we prepare some basic notions or notations about knot theory. The first one is braid group. The braid group is very standard object in knot theory. So as an abstract group, for positive integer n, the braid group is defined by this. So Bn has n minus 1 generators, sigma 1, that are the sigma n minus 1, and they satisfy some braid relations. The braid relations are given by these two types of equations. If indices satisfies this, then generators are commutative. If the difference is just 1, then we have this equation. This definition is as an abstract group, but we can also define the braid group by using picture.
Sorry, Toshiki, what is sigma?
Yeah.
Maybe I miss it out. Sorry.
Sigma is just a generator, just a variable.
Okay.
Element.
It's not concrete.
Yeah, it's just an abstract
abstract setting.
expression. But as a braid groups, we can correspond this sigma as this picture. So braid, the notion of braid was introduced by Artin, and roughly speaking, braid is a kind of this picture. So we first prepare the top ray and lower, and on each top and bottom, we prepare endpoints, and we connect these endpoints by n strings with some crossings.
Like a permutation, but with different setting.
Yeah, actually, it's a
It's not
generalization
one-to-one.
of permutation. We need some information of crossing.
Okay.
Permutation is just forgetting the information of crossing.
I see. Thank you.
For instance, this braid and this braid are different. But as a permutation, they are the same.
Yeah, I see. Thank you.
Yeah. So if we correspond the sigma I, associate the sigma I with this picture, then sigma, if sigma I is this one, then sigma I inverse is this one. So before that, we need to define the multiplication. But the multiplication of these pictures is just a concatenation from top and bottom. For instance, please look the left bottom picture. This is an example of product of two elements, sigma I times sigma j. So here we omit other trivial connections, but the sigma I is crossing of i's and I plus 1's points, and sigma j is a crossing at j and j plus 1. And the product sigma I times sigma j is the concatenation of two pictures. So this is the product. And if I and j are the difference of I and j is greater than or equal to 2, then the product is the same as the product of sigma j and sigma I. Here we allow the continuous deformation. So as a topological object, we get the equation. So this is the first braid relation. Sigma I times sigma j is sigma j times sigma I, if I and j are far from each other. And if the difference is just 1, then this is a sigma I. Other points are just a trivial connection. The vertical trivial connections. Then sigma I times sigma I plus 1 times sigma I is this one. This is a braid. Braid is just like a permutation, but the atom is the crossing information. Then this product is the same as this product if we take a suitable continuous deformation. And they are the relations for the braid group. So as an abstract group, we can define the braid group by this, by using this picture. Then the braid is a kind of set of such kind of pictures, and multiplication is concatenation, and the inverse is just for instance, sigma I, then sigma I inverse is this one. For instance, this is also a braid. And in terms of the generators, we can decompose these crossings for instance, by this picture. So as a topological object, this one is the same as this one. So, and this is products of sigma 2, sigma 1, sigma 3, sigma 2, and 4, 3. So as an element of B5, 5 is now the number of points. As an element of B5, this braid can be expressed as the product of these generators. This is the notion of braid. And by using braid, we can study the knot. For instance, and this one is also the fundamental object, the closure of braid. For each braid, we connect the i's top point and i's bottom point directly. For instance, this one is the example of braid, as I explained before, the 1 to 4, 2 to 5, 3 to 1, and so on, and connect the first point, the second point, the third point, and so on. Then by applying a suitable continuous deformation, then we get this one is the same as the trefoil. Yeah, this part is not trivial for beginners, but yeah, it's just a puzzle. We can get the equivalence between this closure and knot. So by considering the closure, we can get knot, or generally multiple components of knots. And it's the very foundation in the theory of knot, but it's the Alexander's theorem. For every knot, there exists a certain braid such that knot can be obtained as the closure of a certain braid. So we can use the braid to study the knot. And by using braid expression, we define the Alexander polynomial. Yeah, this is the definition of Alexander polynomials. Of course, there are many types of definitions of Alexander polynomials by using the fundamental groups of knot complement or something, but here I introduce the definition using braid groups. The first one is the braid representation. It's a group representation. Bn is a group homomorphism Bn to this space. The quotient is a ring, the Laurent quotient with quotient z. The representation is defined for each generator by this form. It's a diagonal block matrix. And we can easily check that this representation have the eigenvalue 1. So if we consider the characteristic polynomial, it's in linear algebra, characteristic polynomial, this has the factor s minus 1. So by taking the quotient by s minus 1 and takes the value at s equals 1, then we get the Alexander polynomial. And this is the definition. Yeah, up to this factor, but so essentially it's just a characteristic polynomial of plural representation. Yeah, this is Alexander polynomial. Of course, this is not trivial that this quotient defines a polynomial, but Bural or Alexander show that this quotient, yeah, this expression on the right hand side gives a Laurent polynomial.
Can
And this is
take question?
yeah.
Sorry.
Yeah.
So how can you show that this is well defined?
Well defined means this is a polynomial.
Yeah, it depends.
Yeah.
It depends on the existence of limit. So what is the fact behind this?
The fact is here this one.
I see. So for being well defined of this Alexander polynomial. So
Yeah.
you give a.
Yeah, of course we have to check that first. This expression on the right hand side defines a element of this one, and
Yes.
this definition is independent of the choice of sigma.
Okay.
But anyway, they are studied by Bural, or yeah, it's a classical result. So in this talk, I omit everything.
I see.
And I use as a fact.
Okay.
Anyway, by using the important point is such sigma is not unique. So there are many types of sigma, but this definition is independent of the choice of sigma.
Choice. Yes, I see. Thank you.
So then it's an example for the trefoil knot. So in the previous slide, I mentioned that the Alexander polynomial of trefoil is t squared minus t plus 1. So this is calculated as follows. First, as I mentioned, this braid gives a trefoil as a closure. And this braid is expressed by using generators by this form. So then, by computing the Bural representation of sigma, we get the Alexander polynomial. So for trefoil knot, we get the sigma. For instance, we can take this sigma and we compute the sigma 5, beta 5 sigma directly. Since this is a group homomorphism, this is the same as the product of this one. And by definition, for instance, beta 5 sigma 2 is equal to this 5 to 5 matrix, 5 by 5 matrix. The 2 corresponds to the location of this 2 by 2 matrix. And something. And the last one is beta 5 sigma 3. This is given by this. And just by a direct calculation, we get beta 5 sigma is equal to this matrix. So by computing the characteristic polynomial of this matrix and dividing by s-1 takes the limit s to 1, and by dividing a polynomial appeared on the denominator, then we get t squared minus 1. T plus 1. It's the Alexander polynomial of the trefoil. So the calculation is a bit complicated, but we can compute the Alexander polynomial of knot by these steps. So the remaining problem is how to get the braid expression of modular knot. Modular knot is defined as the closed orbit of some flow, and it's very difficult to catch the precise form. But to compute the Alexander polynomial, we need the braid expression. So this is the remaining problem. So in section 3, we prepared the notion of modular braid. This is also already studied by someone. So recall that modular knot, every modular knot is corresponding to a hyperbolic matrix or real quadratic irrationals or indefinite binary quadratic forms. So our aim is from the information of real quadratic irrational, we have to define a certain braid such that its closure is the same as the modular knot. The main idea was studied by Birman and Williams in their study on the symbolic dynamics of Lorenz attractor. Lorenz attractor is an example of chaotic phenomenon. And yeah, motivated by their work on chaotic phenomenon, we define the modular braid from the real quadratic irrational. So we recall that their symbolic dynamics and their braid. So definition for a primitive word in alphabets L and R and something. So I can give a explicit statement of the definition, but here instead of that, I will give an example of the definition of their braid. So as an example, we consider the word LR. So word is just a sequence of the alphabets in L and R. And as an example, I will consider LR, the length 5, and we consider its all cyclic permutations. That means we replace the position of the first alphabet to the bottom. Then, by starting from LR, then the second cyclic permutation is we replace L to the bottom, the R, the LR, and so on. The 5 different words by considering the cyclic permutations we obtain. Then here, then next we assign the order with L and R. The L is smaller than R, and we consider the lexicographical order, these 5 words. So in this case, the LR is the smallest one. The second smallest one is LR. The third one is, so yeah, the first 2 alphabets are the same, RL, and first 3 alphabets are the same, RLR. The fourth one is L, so this one is the third smallest one, the fourth one and fifth one. And then from this information, we define the braid. So by connecting the this ascending order from right to left, left to right. So by this information, we connect the first top point with fourth bottom point from this information. From this information, we connect the fourth top point with the second bottom point, and so on, cyclically. The third top point with first bottom point. And every intersections are assigned as the segment from left top to right bottom is always over than the segment from right top to left bottom. Then we can uniquely define the braid from every word. Then, yeah, this is the braid by using the symbolic dynamics using word, and by using the information about continued fraction expansion, we can get a modular braid. So as you know, the real quadratic irrational have the continued fraction expansion, and it's periodic one. And by considering a suitable SL to Z action, we get W is equivalent to a certain purely periodic continued fraction expansion. And using its coefficient, we associate the word L to the C1, R to the C2, or something. Then, by applying the previous symbolic dynamical braid to this word, we get a certain braid, and we call it a modular braid. Then Etienne Ghys essentially showed that he did not, I think he did not state it explicitly, but essentially he showed that this modular braid defines a modular knot by taking the closure. Its closure is the same as the modular knot. So then, for each modular knot, by using the information of real quadratic irrational, we can get a braid expression. So by combining all results so far, we can compute the Alexander polynomial for modular knots. So for instance, yeah, from the golden ratio, we compute the we show that the corresponding modular knot is unknown. So for golden ratio, we know that this has a purely periodic continued fraction expansion 1 1 1 1 1. So here we take the minimum even period. Then golden ratio is corresponding to a word LR, its length 2, and its all cyclic permutation is just a LR and RL, and the ascending order is just 1, 2, I think. So then by using this word, we get the modular braid 1 to 2 and 2 to 1, and by considering its closure, this is a trivial knot. As for this real quadratic irrational, we know that this has the continued fraction expansion 1 1 1 2. This gives a LR. It's a previous example. So LR provides the modular braid, this one, 1 to 4, 2 to 5, and so on. And as I computed before, this closure gives a trefoil knot. So yeah, for example, we can get knots from real quadratic irrationals by using the Birman-Williams symbolic dynamical braid, and we call it a modular knot. So then finally, I introduce our theorems on the Alexander polynomials. The first one is about the explicit formulas for the Bular representation. Actually, to compute the Bular representation, we have to decompose the braid expression with the generators. So it's a very hard task to compute the Alexander polynomials. But anyway, we get some explicit formulas. For instance, for this real quadratic irrational, the corresponding modular braid is this one. The number of points is 17. The crossings are like this. And first, to compute the Bullard representation or Alexander polynomials, we first have to decompose these crossings with the generators, the product of generators, and compute the products of matrices. And yeah, for this case, we get the resulting matrix is this one, the 17 times 17 matrix. And by considering its characteristic polynomial and something, then we get the Alexander polynomial. But the resulting Bullard representation looks very nice. It's a maybe there should exist a certain formula for this matrix, and the result is this one. So yeah, here I will not give explicit form for a general case, but you can guess from this example. So if we divide the bottom points, classified these bottom points by the direction of the segment. So first P1 class is the point coming from right top, and the second blue class is coming from right top, and so on. According to the orientation, the direction, we classified the points red class and blue class, and let Pi be the number of points of red class and Qi be the number of blue class points in the blue class. So then the matrix can be divided into the blocks. The size is the rows are Q1, Q2, Q3, Q4, P1, P2, P3, P4, and so on. And yeah, in general, for each braid expression, the resulting Bullard representation is given by this form. Therefore, yeah, you have to guess the general form from this expression. But yeah, in this article we provided the explicit formula. So then by using this explicit formula, yeah, of course, from here we need to calculate the characteristic polynomials or something, but by using Mathematica or Python or something, we can easily compute the Alexander polynomial. So by using these explicit formulas, we can observe many numerical experiments or something, and we can get many phenomena, interesting results on modular knots relation, its relations between the modular number theory or topology or something. So the first result is it's just first result is about the degree of Alexander polynomials. By using the explicit formulas, we can get the degree of Alexander polynomial is just the number of crossings minus number of strands. It's just a number of points plus 1. Yeah, for example, this binary quadratic form corresponds to this modular braid, and the number of crossing is the 10 minus 7 plus 1 then. Yeah, these 4 corresponds to the degree. Yeah, this braid, the Alexander polynomial for this braid is degree 4 polynomial, or 1 so on. Here we can see that here this red circle corresponds to the degree, the number of red circles corresponding to the degree. So this alternate sum is just a counting of points, counting of intersections, except for this roof type. You can guess. Yeah, except for this roof, we can count the intersections, and this corresponds to the number of crossing minus number of strands plus 1. But if we, so these 4 examples all gives degree 4 Alexander polynomials, and actually that's all. And if we rotate, so for instance, in this case, there is a sequence of 4 crossing, and if we rotate this picture to slightly, then you can get a Young diagram corresponding to the partition of 4. In this case, means 4, and in this case, 3 plus 1, the 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. There are 5 partitions. There should be 5 partitions of 4, but the missing one is a 2 plus 2. 2 plus 2 is missing, but the reason is if we consider the braid corresponding to 2 plus 2, then the closure is not. It's a very difficult. Yeah, the closure is not. So not. So the 2 plus 2 can never happen as a modular knot. So, but as a corollary, we can get, let AN be a set of Alexander polynomial of modular knots with degree n, then the number of such polynomial is bounded by partition number by the previous observation. In particular, AN is a finite set. Yeah, this is very interesting because if we replace the condition, the modular knot, with a more general knot, general class knot, then it's known that a corresponding set, that means AN dash, is defined as a set of Alexander polynomials of knot, any knot with degree n. Then this becomes an infinite set. But if we restrict the case to modular knots, then the number of AN is finite. So by comparing these results, we can say that the family of modular knots is very small. And an interesting point is here we get the trivial bound, but it's far from the optimal. For instance, in this case, these 4 blades are different, but if we take a closure, then the resulting knots are the same. Or all 4 blades define the same knot. So then the actual number of A4 is just 1. The upper bound is P4 equals 5, so it's very far from the optimal. On the general case, we observed many cases. Here we omit the odd cases, but for n equals odd, then the number of AN is always 0. So I omit. And yeah, this is a list of the number of AN and PN. Here Kn is just the number of partitions of n corresponding to modular knot. For instance, in the previous case, the 2 plus 2 is missing because the 2 plus 2 is not corresponding to knot. So for the case n equals 4, then there exists a missing 1, and the resulting Kn is 4, and so on. So this table suggests our trivial bound is quite far from the actual number. So then the problem is, what is a sharper bound for AN? But I think this question is very interesting and very difficult. For instance, for counts the number of Kn, we need to understand that when the blade defines a knot or multiple component of links. But for instance, we can see that the partition 1 plus 2 plus n defines a knot if and only if 2n plus 5 is a prime number and 2 is a primitive root in this multiplicative group. As you know, the Artin's conjecture says it's an open problem that there exists, there are infinitely many such P. So I think if we can get a kind of simple criteria whether this blade, when the blade defines a knot, then I think such a simple criteria answers the Artin's conjecture. So then this question should be difficult, I think. Or when do 2 partitions define the same knot? In the previous case, there are 4 candidates for different blades, but their closures are the same knot. So there should be a criteria how to distinguish the resulting knot as the same or not. Or of course, the Alexander polynomial is not complete invariant. So there exists a certain distinct knot such that they share the same Alexander polynomial. So we have to understand that when the different modular blades define the same knot or not. But anyway, after understanding the relationship in terms of modular knots, blades, or Alexander polynomials, then finally we have to get the optimal bound But so far, the upper bound is very far from the optimal. This is the first result. The family of modular knot is very small. But compared to this result, the third theorem is the family of modular knot is very large compared to the class of something. Yeah, for instance, for this real quadratic irrational, as I mentioned, the corresponding modular knot is this one. And from the Bural representation, I computed in by the 17 times 17 matrix, we get the Alexander polynomial by this form. So here the character, the point is the coefficients are all +1, -1, or 0, and the signs are alternate. Signs alternate. So from here, we remind that the similar phenomenon for the cyclotomic polynomials. In the cyclotomic polynomials, the first many examples have the same, similar phenomenon. The coefficients are all 1 or +1, -1, or 0 or something. But Suzuki's theorem says every integer can appear as a quotient of cyclotomic polynomials. So then how about the Alexander polynomials of modular knots? The answer is every integer can appear as the quotients of modular knots, Alexander polynomials of modular knots. The proof is very technical, so I skip, but the strategy is very simple. If we consider the sequence of real quadratic irrationals defined by this continued fraction expansion, then the sequence of Alexander polynomials for the modular knots contain every integer as a quotient. But so far, I have no theoretical background for this sequence, or theoretical background for this theorem. But just we found a sequence of the explicit examples of modular knots contain every integer as quotient. And for the alternating signs, for instance, for the torus knot is a very kind of big class, a family of knots. As you know, the Thurston theorem says that set of knots can be divided into 3 classes: the torus knot, satellite knots, and hyperbolic knots. And torus knot is one of them. Or more generally, the L-space knots satisfy the similar conditions. For instance, all quotients of Alexander polynomials lie in this set, +1, -1, or 0, and the sign alternate always alternate. So then how about the modular knots? But the answer is the same sign can appear consecutively for any long, for arbitrarily long. So in this case, the sign alternate, but we can get an example of modular knots, Alexander polynomial modular knots, such that, for instance, the 100 negative sign appear consecutively or something. The proof is also the technical. We just find the explicit sequence of real quadratic irrationals, and this provides an answer. But we have no theoretical background for this theorem. But anyway, these two theorems suggest the family of modular knots is very large compared to the set of torus knots or L-space knots or something. And final one is the PQ torus knot is the set of PQ torus knot is contained by the set of modular knots. So the question is how to which real quadratic irrational corresponds to the PQ torus knot? The answer is very simple and very interesting. The PQ torus knot is defined as the closure of this braid, and the corresponding real quadratic irrational is obtained as follows. So P and Q are coprime, then we consider the grid of size P times Q, and we consider the diagonal and consider the squares such that they intersect with the diagonal. Then we get some sequence of squares, so-called snake graph, and we consider the bottom boundaries and count the horizontal one and vertical one. Then we get, for instance, for the case of 4 times 7, then we get 2, 1, 2, 1, 2, 1, 1, 1, the sequence of numbers. from this data we define the real quadratic irrationals 2, 1, 2, 1, 2, 1, 1, 1. Then this real quadratic irrational defines a PQ torus knot as a modular knot. This is a combinatorial connection with yeah, PQ torus knot and modular knot. Yeah, and more. So we have many other examples of not invariants or number theoretic invariants. But yeah, I think the second one is a bit interesting. But it's no result and essentially shown by Hilsebus, Zagier. But for a prime number P satisfying these two conditions, then we consider the modular braid for square root P. For instance, P equals 31, then the resulting modular braid is this one. Then, as before, we separate the bottom point with the P part, Q part, then take the alternate sum, then this is essentially equals to the class number of imaginary quadratic fields. Or and so on. This braid knows the information about the class numbers. But essentially, this is the result by Hilsebus and Zagier. So there are many questions. For instance, we don't know what is the degree of Alexander polynomials in number theory, or what is the role of Alexander polynomials in number theory. So in this talk, we just provide the how to compute the Alexander polynomial modular knot and observed many things. But so far, we couldn't find any relationship between number theory and topology. And yeah, so our ultimate goal is by using modular knots, we, for instance, prove something in number theory by using topological idea, or some topological problem by using number theoretical idea, or cultivate new frameworks of the arithmetic topology or something. But so far, it's just the first step, and we just compute the Alexander polynomials. Or of course, we have to consider the more general types of not invariant, for instance, Jones polynomials, Humphrey polynomials, and so on. But the one interesting point is Kentaro Okamoto. He was a student in Kyushu University. In his PhD thesis, he considers the braid zeta function by using the braid representation of braid group, for instance, the Bulau representation or some other braid representations corresponding to Jones polynomial or something. And he considered similar to the characteristic polynomials as zeta functions and studied some analytic aspects of such functions. For instance, the locational poles, zeros, or something, functional equations or something. So by combining these objects, I hope that there are many interesting results in this theory of modular knots, but it's just a first step. So if you have many other ideas or something, then please try or share with me or something. Yeah. Sorry, it's late, but yeah. Thanks so much.
Thank you very much for very interesting and very interaction between different branches of mathematics. It was really interesting. So maybe let me first ask for the participants. Are there any questions or remarks for this great talk? Actually, I have one question, but it's very, very raw. I mean, it's not very well cooked question. So sorry, maybe for this stupid question, but as we know, theta series of quadratic forms are actually modular forms, and in this case, we can present it as a Fourier expansion, and this Fourier coefficients have a lot of arithmetic informations. Do you expect any relation between these it was binary quadratic forms, and any arithmetic information about this modular nodes and Fourier coefficients? Sorry if it's a very bad question, but it's a very broad question.
The point is the modular knots are corresponding to the indefinite quadratic forms. So that's the problem. The classical theta function are defined for the positive definite quadratic forms. So yeah, of course, by applying the theory of mock theta functions or Tsubigura's result, on the study of modular indefinite theta functions, we can define the theta functions, but so far they are different topics. So yeah, I hope that there should be a connection with some because all our study on real quadratic irrationals or indefinite binary quadratic forms. So then all should connect to each other. But yeah, so far I have no idea how to get for instance, the information about modular from the indefinite theta functions.
I see.
And so on.
I see. Thank you. More questions or remarks? Do you have some thank you messages on chat?
Yeah. But anyway, so far everything is questioned on
It's very
modular.
open. Yeah,
Yeah.
it's very open. It's very open.
Yeah, so yeah, I hope it becomes very interesting topic.
Hopefully.
Yeah.
So I think we don't have any questions or remarks, but we have thanks messages again. So thank you very much for the speaker again for this very interesting talk. It was our pleasure to host you, Toshiki. Thank you.
Yeah, thanks so
And
much.
by the way, this was the last talk of 2025. I wish you everyone a happy new year, and let's hope that 2026 will bring us nice theorems, good results, and more important, with good health. I have a small announcement. The first talk and the next talk, the first talk of New Year and next talk will be given by Professor Andrzej Dujella on 13th of January. So thank you again, Toshiki. Please say hello to all my people in Kyushu that I met in April, and hopefully see you soon again.
Yeah. Thank you.
Thank you. Have a nice evening. And also we have Rio from Tokyo. He's our regular participant, Rio Sadamatsu. He's from Tokyo. He didn't miss any seminar. Arigato gozaimasu, Rio and Toshiki. Okay, see you in next seminar.
Yeah. Thank you.
Bye bye.
Bye.